Sandeep Sahani, Head, Center for Climate Research, Singapore, and faculty, Center for Atmospheric Science, IIT Delhi. Last, not the least, I welcome all the participants, faculty members to this international webinar on an overview of climate change assessment, global to regional. I welcome once again, I welcome all you to this international welcome webinar. Have a nice day. Thank you.
Thank you, sir. I would now like to request Professor Dr. Jeevananand Jaina, sir, Principal, GIET Bhubaneswar, to kindly speak a few lines. Sir, please.
Thank you, Rajeshri ma'am. A very good afternoon to one and all. Guest of the day, respected Dr. Sandeep Sahani sir, scientist, Center for Climate Research, Singapore. Honorable competitives through their active participation with the outside world. The framework and the competency which has developed, working within that, we all brought excellency for our institution in curricular, co-curricular, and also in extracurricular activities. So those who have contributed directly or indirectly for the growth of the institution, we acknowledge to each individual. We too feel proud for our esteemed alumni who are working on various prestigious industries at all corners of the globe. We are proud for our faculty members, for our non-teaching members, and for all the stakeholders, those who are directly and indirectly contributed their part for the all-round development of our institution. In recent past, our institution was accredited with A+ grade by National Accreditation Assessment Council, Government of India. So this is all reflected because of the hard work and sincere effort of our family members. So all the credit goes to our management, our family members, and to all our stakeholders. We, the staff members, the students, and the alumni are quite confident and promising to elevate the flagship of GIET to a greater height and to see the name of our institute in the top list among all private engineering colleges. So last but not least, once again, I welcome you all to this international webinar, and a special welcome to Dr. Sandeep Sahni from my own behalf and on behalf of GIET for his present, because of his valuable time, because out of his busy schedule, he present with us, and he will present and he will share his knowledge and research work with us. Thank you. I hope this technical session will be definitely an interesting technical session for you all. Thank you.
Thank you, sir. Thank you for your valuable words. It is not only a pleasure but honor to have among us Dr. Sandeep Sahni, sir. He's an assistant professor in Center of Atmospheric Sciences, IIT Delhi. He has completed his PhD in Atmospheric Sciences from Indian Institute of Science, Bangalore. He is presently the head of Climate Modeling and Prediction, Center of Climate Research, Singapore. His areas of interest lies in climate modeling, climate change, and Asian monsoon. He has received many awards and honors like S.K. Banerjee Young Faculty Initiative Award from the Ministry of Earth Sciences, Government of India, Faculty Research and Travel Award from IIT Delhi, and many more. I once again welcome you, sir. I would like to request Sir to kindly proceed towards the technical session. Sir, please.
Thank you, Rajeshri, for the kind introduction. So I'll just share my screen first. Just give me one moment. So is this visible? I just want to check. Can all of you see my slide?
Yes, sir.
Okay. So to start with, I would like to thank Professor Jaina, Principal GIET, and Professor Mishra for inviting me to speak at this webinar, and also the senior management of GIET. Thank you so much. And also the participants for taking time out to come and attend this webinar. Of course, I would have loved to be there and interact in person, but I mean, given the circumstances, this is the best we can do. So I'll be speaking about an overview of the climate change assessment process, the way it is done from at global scales to regional scales. This is, yeah. So this is the brief outline of my talk. I'll start with what's the basis for climate change concern. And then I'll talk about IPCC, that's the Intergovernmental Panel on Climate Change, a UN body. Then I'll talk about what climate models are and how they are used for climate change assessment at global and regional levels. Followed by that, I'll talk about uncertainty in climate change projections and then limitations of climate models. After that, I'll just speak a few, maybe a couple of slides on what is this? Can you see this? Hello? Sorry.
Yes, sir.
Okay, sorry. I mean, I saw some lines drawn on my screen, so I was kind of afraid what is going on. Anyways, so I'll end with some takeaway notes. Sorry, I mean, these are all very new things which all of us are doing, so there may be some technical glitches here and there, so let us excuse each other for that. So what's the basis for climate change concern? So this shows two graphs basically. One is for the carbon dioxide levels. The x-axis is in thousands of years. So it's almost a million years, starting from a million years to something good. Sorry. All right. So the x-axis is the time axis, and y-axis, we have two y-axis basically. One is the carbon dioxide levels, and here we see the temperature anomalies. That's anomalies meaning deviations from the mean, basically. There is a base period, and what are the deviations from the mean. So what we can grossly see from this is whenever the carbon dioxide, there is a, 1-to-1 relationship between carbon dioxide levels in the atmosphere and temperature. So whenever carbon dioxide level goes up, temperature goes up, and whenever it comes down, temperature goes down, and this has been going on. So right now, the current carbon dioxide levels, so this is kind of slightly outdated, but the current levels are around 420 parts per million. So we know this has happened, and then this might follow. So and then it's not just about the temperature, but once the temperature changes, there are many other things which change along with the temperature, whether it's a sea level rise or the extremes in rainfall and heat waves and whatnot, and all kinds of changes associated with temperature changes. So this shows the carbon dioxide concentration of observed at Mauna Loa Observatory over Hawaii. So this has been a continuous observation starting from around 1960s till current. It's called as a Keeling curve. So if you see, this has been continuously increasing, and approximately the current values are around 420 parts per million. So it's measured over a single location, but it is kind of representative of what the entire the atmosphere, because carbon dioxide is a well mixed and long lived gas. The pre-industrial values, that's around 1850s or so, the values were around 280 parts per million, and the current values are around 420 parts per million. So almost a 50% increase. If we see this in the form of an animation, so this is called as the atmospheric CO2 spiral, done by Ed Hawkins, a famous climate scientist from the UK. It starts from around 1960s, and we see how it grows. So this is the way it has been growing, starting from 1960s onwards, and this is till 2017. So we are seeing the level is around 407, but the current levels are around 420 or so. So this is the CO2 spiral, and this is the temperature spiral done by the same person, Ed Hawkins from the UK. And we see from 1850s onwards how the global mean surface temperature has been changing in time. And we see two circles outside. This is 1.5 degree and the 2 degree circle. So these are basically as per the Paris Climate Agreement. So the international community is trying to restrict the global warming to 1.5 degree and at most at 2 degree levels, because after that the changes in our climate would be phenomenal changes we might see. So the international community wants to restrict the global warming. That's the global mean surface temperature changes. Of course, the local changes can be larger than this, but at a global mean level, these are the targets, basically the temperature targets of the world. And this is where we are, very close to our targets. So in some sense, not much time left. I mean, we have to act on things fast. This is from NASA GIET, that's the Goddard Institute of Space Studies. They have these temperatures observations starting from 1880s onwards till current. And then here we see two lines. One is for the oceans, just the water points, and then this blue line, and then the red line is for the land points. So we see that the land has been warming at a faster rate as compared to the oceans, primarily because of the low specific heat capacity. So I'll move on to what IPCC is. So it's, as I told earlier, it's the Intergovernmental Panel on Climate Change. What it does is it comes up with these assessment reports every 6-7 years, which summarizes the observed and projected climate change over the world and their impacts, and also suggests adaptation and mitigation strategies based on published literature. So it doesn't do any research of its own. Rather, it summarizes the findings that scientists across the world work on. So it's basically an intergovernmental body of the UN to provide scientific information for understanding the scientific basis of the risk of human-induced climate change, its impacts, adaptation and mitigation strategies. It was established in 1988 by the WMO and the UNEP, and was later endorsed by the UN General Assembly. So it's basically a consensus-based approach. I'll show what a consensus-based approach means. This is a recent tweet from the IPCC. So this is the last assessment report was called as Assessment Report 5, which came out in 2013-14. And then the next assessment report is called as the Assessment Report 6, which will be coming out mid of next year. So before it actually comes out, it goes through a very stringent review process. So this is the SOD, stands for the second order draft. So it's still under review. So you can see, I mean, there are more than 1,200 expert reviewers across the world from 82 countries and 42 governments, and then over 50,000 comments. So there are review editors who will kind of coordinate with the authors to make sure that the comments are addressed in a scientific way. I was also one of the expert reviewers this time for the second order draft. So this is what the IPCC does basically, and then for climate, because we're talking about, so there are two things. One is the observed climate change, which can be assessed based on observations, whether it's satellite observations or ground-based observations, and many other observations. And there is other thing, which is the climate change projections. So we want to know what will happen in the future so that we can prepare for it in advance. So for that, the only tools that we have with us is something called as climate models. So what are these climate models? climate models are basically, we want to model the Earth system, the climate system basically, and it's a mathematical model. So what we do is we divide the Earth's atmosphere, land, and ocean into a three-dimensional space. So into regular grids basically, and then there are equations which we solve on these three-dimensional grids. So these, when I say solving means, so these are all nonlinear, couple PDEs. I'll show what they are, and then so we integrate in time basically. So over all these, and then as a part of the solution, we have the variables, which say rainfall, temperature, winds, humidity, and so on over each grid point that we get as outputs of these models. So this is another picture which shows a similar thing basically. So we divide. So the Earth system is divided into these grids, and then so this is the horizontal, and this is the vertical. So this is a sample from one of the atmospheric models. So there are around more than there are around 90 or so climate models taking part in the assessment report 6, for example. So there are so many climate modeling centers spread across the world. So they do all these climate model runs using these climate models. So these climate models have physics, mostly physics, and then some amount of chemistry and biology in them. So there are all these processes that we are seeing are actually converted into some form of physics and then mathematical equations which are solved. So these physical laws, like say conservation of mass, momentum, energy, and the thermodynamic properties, and so on, there are corresponding equations for these, like momentum equations, continuity equation, equation of state, and all these equations are there, and these are solved. So this is a very simple way of showing these equations in just x, y, and z coordinates. The real equations are actually in spherical coordinates, which are much more complicated. But then I just wanted to give you a feel of how the equations look like. So what we try to do in these models is, on the left you will see a tendency term, that's the rate of change with respect to time. On the right you will see some advection terms and some other terms, some forcing terms. So we want to know the rate of change in time. So given we have an initial state, we compute the rate of change with respect to time. And then once we know the rate of change with respect to time, we multiply that with something called as time step. That gives us the delta change. So the initial state plus the delta change gives us the final state. So this is what, in a nutshell, this is what climate models do. And then so these are a set of couple PDEs, that's a partial differential equations, and we try to numerically solve them. By solving, I mean we basically integrate them in time. So if you see this graph below, so we have initial conditions, we have boundary conditions, and we integrate in time. We keep jumping. So a typical, say, time steps are around 30 minutes for around 100 kilometer grid sizes. So we jump, say I want to do a climate run for say for one day, for example. So I have to take 48 jumps of 30 minutes each to do my 1 day simulation. And if I do want to do the same for say 100 years, I have to do many jumps to actually do a 100-year run. So although this is briefly what it is, but in reality it is way more sophisticated. So I mean, say dozens or maybe a few dozen of people working for say 20, 25, 30 years work and then develop a climate model from scratch. That is the kind of effort and expertise required for that. So this is a sample which on the y-axis, you see a bunch of different climate models. On the x-axis, you see thousands of lines of code. So say, for example, this is one of the models of the US model called as CESM. So this is kind of outdated. I mean, this figure is, say, 10-year-old. I mean, as of now, it's more than 1 million lines of code. So that's the kind of complexity involved. And these models, we don't run these models on our laptops or workstations. These are mostly done on supercomputers. So we install these models on the supercomputers and integrate them in time. And then once we have outputs, we analyze them. So the typical model outputs are like, say, rainfall, temperature, winds, humidity, and so on various time and space scales. So we have this data for each grid point, which we saw before. So say, for example, there are many uses of these climate models. Say one of the questions, for example, that which people generally ask is whatever climate change we are seeing is whether it is kind of a natural variability or it is actually anthropogenic, meaning human-induced climate change. So say, for example, if you want to answer these kinds of questions, so don't get overwhelmed by all these figures. I mean, just look at the last on the last row, first panel, which shows just the land surface temperature anomalies or the temperature changes. So you will see two sets and one black line. That black line is actually observations, and then two sets. In one set, that's a blue set, we run the models with just natural forcings. That's just the solar radiative forcing. That's a solar forcing which is coming from outside, and the volcanic forcing. So these are the two natural forcings. And then if we do that and run our models, you will see that we are not able to simulate the observed temperature change. Yeah. So this blue shade is well separated from this temperature change that we see from observations. But if we have all the forcings, that is anthropogenic forcings included, we are able to kind of get the models are able to simulate the kind of changes which we actually see. So what does this prove? This proves that anthropogenic emissions play a major role in the climate change or the temperature changes that we see. So this is one of the uses of climate models, for example. And there is, having said that, there is uncertainty in climate change projections. So it's not that everything is that we say is certain. We are sure of this is what will happen. Definitely, it's not like that. There is uncertainty, but then there are ways to quantify this uncertainty as well. So when I say uncertainty, there are basically three broad categories of uncertainty which we deal with. One is called as the initial condition uncertainty, which is not very important for the climate change projections. This is mostly important for the numerical weather predictions. Say, I mean, I want to do a 2-day or 3-day or 4-day run. I mean, a short range weather forecasts. This is important. But for the longer range projections, what is important is the model uncertainty and the scenario uncertainty. So say, for example, I want to do a weather forecast. I don't have to think of what the scenario would be tomorrow. I just have to do a weather forecast. I mean, I have initial conditions and then initial and boundary conditions. I just run my model. I get something for tomorrow. I mean, well, this is how the rainfall would be, temperature would be. But when we talk about climate change projections, say 100 years, we have to think in terms of scenarios. I mean, how the deforestation would happen in the next 100 years, how the energy matrix would change in the next 100 years, how the land use, land cover would change in the next 100 years. So this is something which the social scientists do, and they come up with this with various socioeconomic storylines, basically. And these socioeconomic storylines are converted into scenarios. So scenarios meaning, I mean, so given this socioeconomic storyline, what would be the carbon dioxide levels in the atmosphere, and based on those carbon dioxide levels in the atmosphere, how would the climate system respond to those? So that is called a scenario uncertainty. And then there is model uncertainty. I'll show you what model uncertainty means. So before I go to model uncertainty, so this is what scenarios, I mean, what I was talking about. So on the y-axis, you see carbon dioxide equivalent levels. So, and these are 4 scenarios which were used in assessment report 5. So they are called as RCPs, or the representative concentration pathways. Concentration of what? Concentration of greenhouse gases. So all greenhouse gases are expressed as carbon dioxide equivalents. So this is called as RCP 8.5, or the business as usual, or also called as a worst case scenario. This is called as RCP 6. This is called as RCP 4.5, and this is called as RCP 2.6 are the best case scenarios. So the worst case scenario assumes that there will be absolutely no mitigation efforts by any of the governments, whereas the best case scenario assumes that there will be a lot of mitigation. Mitigation meaning efforts to reduce our emissions. So that is what mitigation is. And then there are 2 intermediate scenarios in between. So these are various scenarios. So say, for example, you take a model, any of the model, and you run your climate model you do a 100-year, say, simulation with 4 different scenarios. You will get 4 different answers of, say, temperature projections. So these 4 different answers that you get for, say, temperature projections using the same model, this is called a scenario uncertainty, because you are getting 4 different answers. using the same model because the scenarios are different. So this is called as scenario uncertainty. If you use one scenario, for example, and you run the same scenario for, say, 10 different models and you get 10 different answers, that is called as model uncertainty. So I'll show an example of model uncertainty. So in this figure, we are looking at the rainfall change under global warming. So we have used the worst case scenario here, RCP 8.5. We are looking at the June, July, August rainfall change, end of 21st century, as compared to a baseline period of the current climate. So this is for one of the models. We look at the changes. So below you will see this the shading, that's the color bar. This talks about this shows the magnitude of change that you see. So with greens and blues for positive changes and yellows and reds for negative changes. So this is what you get from one model. If you look at another model, you get a different answer. You get another model, you get a different answer. So this is what I mean by model uncertainty. Different models will give you different answers, not because they use different physical laws or anything, but there's something called as parameterization schemes, which we do for processes which are smaller than the grid scale. So their kind of different modeling groups do it in different ways, and because of that, we get different answers by different models. That is one of the major reasons. That's called as model uncertainty. So when we do climate change assessment at a global level, so there's an example of assessment report 5. That's, as I said earlier, the assessment. So this is the last assessment report of the IPCC, which came out in 2013, 2014. And the next assessment report will be coming out. That's AR6 will be coming out mid of next year.
I know.
So this is the projected change in annual mean surface temperature. This is shown for two scenarios. So this is the RCP 2.6 is the best case scenario with a lot of mitigation efforts by governments. And RCP 8.5 is the worst case scenario where when there is no mitigation, it's one of the business as usual scenarios. We don't do anything about things and just let things evolve the way things are going on right now. So we can see that they are very different from looking at the colors. So RCP 2.6, we have less of warming. RCP 8.5, we have a lot of warming. And then we'll see that on these figures, we have these kinds of hatching. That's these lines here. And then we have something called as these dots called as stippling. And then there's where we have neither of them. There is neither hatching nor stippling. So these are ways of handling the uncertainty. So what does this mean? So there is a lot of statistics goes into it. So I'll not go into the details because of the time now. But say hatching means we are confident that the changes are smaller than natural variations. So although there is a change, we are confident that this change is not really something which we can call as climate change. This is well within the natural variability of the system. So what is natural variability? Say, for example, even when there was no climate change, there was no the carbon dioxide levels were not changing, still then we saw that there was this increases and decreases of carbon dioxide levels and temperatures. Those were the natural changes basically. So those are so hatching shows that we are confident that the change is small and within the natural variations. Where we see stippling, that's the dots that we see, we are confident that the changes are higher than the natural variations, and most of the models agree on this. So model agreement is kind of used as a way to reduce it, because only when the majority of the models, say 90% of the models, agree on a sign of change, we are confident that, okay, this change is a real change. If say 50% of the models say one sign of change, other 50% of the models say another sign of change, then we don't do, we are not confident about what the models tell us. So in those kinds of situations, for example, we say that we don't know. So wherever you will see neither dots nor those hatches, the answer is we don't know what is going to happen. So this is the case for temperature, and this is the case for precipitation. So if you say, or rainfall. So say, for example, one of the things I would like to point out for you here is, say, if you look at RCP 8.5, that's the right panel. If you look at India, you'll see that there is most of it is neither hatching nor stippling. So neither we are saying that there is no change, nor we are confident that there is change. So this could be because the change is smaller than the natural variations, and the models don't agree on the sign of change. So there is a lot of, because in general models, I'll show later that the models find it very difficult to simulate Indian monsoons, for example, because it's quite a complex process. So these are the kind of challenges, and these are the way uncertainties are handled in these reports. So I'll just give you an example of regional climate change. So this is something which we did last year with one of my postdocs at IIT Delhi. So what we looked at is, this is for one of the global warming scenarios. That's the worst case scenario, RCP 8.5. We took a model and we just computed, say, one is for this black line is for natural. That's the changes which we are seeing in the current climate, and this just shows the probability distribution function of rainfall over each of the grid points. The x-axis is rainfall and y-axis is the probability distribution function. So this black line is natural, and for each, and we compute the period during which we see the warming. Say you run the model for 100 years, so it will, before it reaches, I mean, it will go through a range of warming till it reaches, say, 4 degrees or 5 degrees of warming at the end of the 21st century. So if you kind of bin them into, say, 1.5 degrees Celsius, so different scenarios, I mean, different temperature times, I mean, temperature change times. So when the period when the 1.5 degrees Celsius change happens, the period when the 2 degrees Celsius change happens, when 2.5 happens, when 3 happens, and so on. So if you keep doing that and looking at the PDF of each of these, what you will see is, one is we are going into a regime of unprecedented events. Yeah, so we will be seeing events which we have never seen before. So in simple words, the intensities would be increasing significantly. The other thing that we see is, even for the worst case events which we have experienced till now, their frequency will increase significantly. So this was kind of one of the, so we have to be prepared for that, basically. So models are giving us guidance that this is how things could change, and we have to be prepared for it. And what we see is, with warming, things become more and more worse. So warmer the temperatures, worse. I mean, it's not just about the temperatures, even in terms of rainfall and many other things become worse. So what are the limitations of climate models? So what this figure shows is, on the top panel, the first panel, it shows June to September rainfall from India Met Department observations, and each of these panels are basically there are different models. So we are looking at the biases in the models. That's the, I mean, if you do a model minus observation, you come up with the biases. You might, I mean, you can also consider them as errors if you would want to. So so the more blues and reds you see, the more are the biases of these models. So you will see that different models have different bias patterns, and the bias patterns are really large. So the bias patterns are really large. So that means that the models have to be improved. Yeah, that is one thing. So because model improvement is a slow process, you can also, there are ways of post-processing your model outputs before you actually use them for any decision making in terms of, adaptation measures. For example, if you want to take or do a risk assessment or impact assessment, you want to first post-process this global model outputs before you actually use them. So as far as model improvement is concerned, for the first time in India, there are ongoing efforts at the Indian Institute of Tropical Meteorology in Pune, which is a part of the Ministry of Earth Sciences, to have our own model. So India didn't have its own model till now. Yeah. Very recently, India actually had its own model. And for the very first time, we actually participated in this. We also did our runs, and we gave this runs for the international community to analyze and so on. So IITM has been doing it, and also there is a parallel effort at IIT Delhi, which we are doing for model. Hello? Hope you can hear me. I think I got muted somehow by the host, probably. Anyways, so I'll just continue. So there are two parallel efforts in terms of model improvement, one by IIT Pune, part of MOES, and one at IIT Delhi, which we are leading. And I'll just show you. So this is called as the DC Center of Excellence in Climate Modeling at IIT Delhi, which is a part of the National Mission for Strategic Knowledge on Climate Change. So the PI is Professor S.K. Mishra. I'm the co-coordinator of the Center of Excellence in Climate Modeling, and we have Professor Das as one of the co-PIs. It's quite a big team, actually. We have 7 co-PIs, 25 students and project scientists, and 10 associate faculty, and so on. So the objective is to come up with to develop an India-centric climate model. So when I say develop, as I mentioned earlier, when we say develop, it's not like really developing from scratch, because if we try to develop from scratch, we need around, say, a couple of dozen people working for 20-25 years to develop from scratch, and we don't have there is no point reinventing the wheel, basically. So we take a model which is performing reasonably well over the Indian region, and then we kind of make improvements to this model to reduce the biases that we saw. So this is the India-centric. So we are developing in this India-centric climate model, which with an objective to reduce the biases in simulated temperature and precipitation distribution over India. And these outputs, when we do the runs and so on, it will be used for various impact assessments and so on. And also, one of the objectives is to develop trained manpower, because there are very few manpower who can actually do these kinds of things in terms of model running models and model improvement and so on. So the other thing which I mentioned, if you remember, one was model improvement, the other was post-processing. So post-processing, there are various ways. One is, say, one of the things is downscaling, and there is bias correction, and there are, so these are the two major things which are done before you actually use the data. So this is what downscaling is. So there are two major ways. One is dynamical downscaling, and the other is statistical downscaling. So what is done is, so we know that there's a socioeconomic storyline, or the scenarios basically that we have. So we saw 4 scenarios, for example. So there are the scenarios, which means there are 4 various climate, carbon dioxide and other greenhouse gas levels in the atmosphere, which are used to run these global models. And then we have climate projections. It's a global projections, and then we either do statistical downscaling using observed climate, or do dynamical downscaling using regional models over smaller domains and come up with downscale projections. So what is the necessity for this? The necessity is decision makers need information at much finer scales so the needs of decision makers to plan for climate change at the regional level are much finer than what is provided by the global climate models. The coarse resolution climate change projections need to be translated into finer spatial resolutions. So downscaling refers to this method of translating coarser scale climate information to finer scales. And then, although this is standard practice, there are a variety of assumptions behind these techniques that are used to derive such fine scale information. So say, for example, I'll just give you an example of dynamical downscaling. So at the top, you see a global model run at a coarse. So when I say this 1.32 degrees, it means the size of the grid box is 1.3 by 1.3 degrees, which converts to approximately, say, 130 by 130 kilometer in X and Y directions. So it's more than 10,000 square kilometers for just one grid point. Yeah. So if we just did that, and we just kind of regridded our, so if we did that, we have to compare this with the bottom right-hand panel. That's the observations. So we see that the fine scale features that we see in the observations are completely missing in the top panel if we have a coarse model. So if we run it in a finer resolution, it kind of somewhat captures these fine scale features which we see in observations in the bottom right-hand panel. If we further increase the resolution or reduce the grid sizes, we are closer to observations. This is because one of the major reasons is the coastlines and the topography, that in terms of mountains and land use, land cover, and the coastlines get better represented in these models. So because of that, your simulation quality increases. So we have to do this as, for dynamical downscaling. But then why we don't do it at global level is because it is too expensive. So what we do is we take global models and we force the global model we force the regional models at high resolutions with this global model data to come up with these kinds of forcing, downscaled outputs over regions of interest. So having said that, so this is one of the things, and of course I will not, time is too limited to actually talk about bias correction and all that. So I'll finish maybe in 7 minutes or so. So while climate models give us rainfall, for example, they will not tell us whether this rainfall will lead to a flood or not. And you have to do another set of things called as impact modeling. For that, you have to use another set of models called as hydrology models. Okay, so climate models tell us about rainfall over a location, not whether the given rainfall would lead to flooding or not. That would you will have to run a hydrology model for that to find out if the given rainfall would lead to flooding in terms of surface runoff, inundation, etc. One needs to run a hydrological model. So the challenge is hydrological models work on much finer spatial scales, resolutions. It's a few hundred meters basically, and the global model is giving you data at say 100 by 100 kilometer grid. So you have to first do a downscaling and then use this downscale data to force your hydrological model if you want to know whether a given rainfall would actually lead to flooding or not. So I'll end with these takeaway notes. First thing is extreme events projected to increase in general with warming, although some regions will be affected more and some regions will be affected less, but overall extremes would increase. So general climate change outlook for India is increase in heavy rainfall, extreme events, and droughts, droughts and extreme rains are kind of two sides of the same coin. When you change the distribution and both happens. On the one hand, extreme rain increases, and then on the other hand, you have a lot of consecutive dry days leading to droughts and so on. And then you have increase in heat waves, there is sea level rise, which is primarily because of two reasons. One is because of the ice melt, say the Greenland ice melt, and then the Antarctic ice melt, which is leading to more ice in the sea, which is leading to sea level rise. And the other reason is the thermal expansion of the water because of increased temperatures, which is leading to sea level rise. And at local levels, of course, there is some subsidence of lands as well, which can lead to sea level rise and so on. And cyclone intensity, for example, is kind of projected to increase. Orissa, for example, is especially vulnerable to many of these things. Whether it's rainfall extremes or droughts or heat waves or sea level rise or cyclone intensity, storm surges. Orissa is actually vulnerable to all of these things, we know. So we have to be better prepared for all these things. And then global and regional models provide us best estimates of what to expect. They're not really, they don't tell us that this is what will happen. They give us guidance that this is all that could happen. And so we have to prepare accordingly. Although models have improved significantly, they still have biases at the global and regional scales. Parallel efforts are on to improve the models as well as to post-process the model outputs to make them more usable for impact assessment and adaptation planning. So, say for example, even if we didn't have the models, the best starting point in terms of disaster preparedness is ability to manage disaster risk due to the worst extreme event in recorded history, for example, whatever worst extreme event that may have happened in that location in the recorded history, to be prepared to handle it well. Also, details matter. For example, the same rainfall event which happened, say, 20 years ago, if it happens again, it might lead to a different level of flooding. Why? Because the land use, land cover change may have changed because of urbanization, which would change your flooding. The kind of flooding that you see. So all at the gross level, all the things look very simple, and when you go into the finer details, there are more and more and more nuances of all these things that we see. So with this, I would end, and I would thank you so much for your attention. So I was told that there will be some questions which I will see in the chat box. So with this, I end. I'll stop sharing my screen. All right. So if there are any questions, I would be happy to answer. So do I have to look at the chat box? So I'm just scrolling through the chat. Basically, I'm just looking at. I'm just hunting for what all questions are there. Okay, I'll share the PPT. There is a request to share it. Okay, I'll do that, and then. The next solar cycle becomes less active, will be good. Okay, so so I see an interesting question. Okay, so what happens if the next solar cycle becomes less active, will be good? So the ice age thing is not because of the solar cycles, but it's mostly to do with the eccentricity of the axis of the Earth, basically. So in terms of, if you're talking about the solar radiation that is coming in, so one of the things which say climate skeptics say is no. I mean the emissions that we that human beings are, I mean, what emissions we do that is actually not responsible for the climate change, and it's just because of there are changes in the solar radiations, because of which we are looking, which we see this temperature changes. But there is a figure on NASA's website. If you can see, the solar radiation actually changes by very little. It's between 1360 to 1361. That's just 1 watt per square meter change. And as of now, say last 20 years or so, the solar radiation is actually decreasing. Slightly though, I mean in a very small range, but the temperatures are increasing. So on the time scales that we are talking about, solar radiation is not the the incoming solar radiation that we have, that is the solar cycle is not the major reason. But on geological timescales, yes, if on geological timescales, there will be an ice age even in the future when the eccentricity of the Earth's axis changes. Yes, that will be. But that is not exactly what we call a solar cycle. Okay, so next question is from Dr. Pankaj Mittal. How can we manage disaster? So as I said, I mean, to manage disaster, of course, the disaster, the NDMA, for example, the National Disaster Management Authority and the Disaster Response Force is there. They look at all these things and they manage a disaster. So one of the starting points, even if we were to trust or not trust these climate models, that is fine. But the starting point would be, if the same exact event happened, are we prepared to handle the same event? Say, for example, the 99 super cyclone which happened. I mean, a lot of changes in the disaster management happened after that in Orissa, for example, which led to a much better disaster response preparedness. So that is, yeah, I mean, so as a starting point, we can actually use how prepared we are to handle if the same thing happened again. And then we can look at, say, these projections. If, say, the frequency, say, for example, whatever the maximum rainfall, the most extreme that may have happened, if the frequency increases by 10 times, for example, or the intensity increases by 50%, how can we handle that? So these are the kinds of things which we have to see. When the information that is coming out from these assessment reports and the climate models, we have to see what is the local impact. So what is the impact over Odisha, for example? And if this kinds of, if the precipitation frequency increases and intensity increases, are we prepared to handle it? That is something which the disaster response force and the disaster management authority does actually. I have one question. Different models have similar physical conditions or initial conditions, but it shows different outputs. Yes. So from Dhanya, so different models have similar physical conditions, initial conditions, but it shows different outputs. Yes, that is true. Because as I said, so there are two things. One is something called as one is the grid. So as we saw that we are actually discretizing a continuous system. Yeah. So the system is actually continuous, but we are discretizing into grids. So whatever happens on the grid scale, we understand that, but whatever happens at the subgrid scale or at a spatial scale, which is less than the grid, we have to do something called as parameterization, and different modeling groups do this parameterization in different ways, and that kind of changes your model outputs. That is why we get this model uncertainty, which I said. And then next question. So Dr. Mishra, please let me know when I have to finish, because I see 33 new messages. I'm not sure how many questions are there. And of course, given the time we have, we may not be able to answer all the questions, but of course, feel free to, just send me an email with whatever question you may have. Maybe one more. Sorry?
Now, all the participants are requested, if any questions are there, we will give all the answers through the mail. Please drop the mail in my mailbox or drop the mail Dr. Sahani mailbox, so that I will share all these things to your queries. We will conclude the session. If anything you want to share, then you can share these things. But for our side, we will request all the participants, whatever the questions, please drop in my mailbox, so that I will convey to the doctor to you. Thank you, sir.
Okay, thank you, Professor Mishra. Yeah.
Thank you, sir. Thank you for your valuable words and your expert opinions. I'm sure it will enlighten all our participants in this field. With this, I would like to request Professor Binay Kumar Paningrai, sir, HOD Civil Engineering and co-convener of this webinar, to kindly give the vote of thanks. Sir, please.
Thank you, madam. A very good afternoon to one and all. I am Professor Binay Kumar Paningrai, co-convener of this webinar. It gives me immense pleasure to thank each and every members associated with this webinar. First of all, I would like to thank Honorable Chairman, Gandhi Group of Institution, Professor Dr. Satyaprakash Panda sir, for encouraging us in conducting the webinar. I would also like to express my gratefulness and thanks to revered Vice Chairman GIET Bhubaneswar, Professor Jyoti Prakash Mishra sir, and Professor Snigdharani Panda Madam, Secretary GIET Bhubaneswar, for believing in us always. I also special gratitude and thanks to Professor Dr. Sandeep Sahani, Scientist, Center for Climate Research, Singapore, for accepting our invitation and gracing the webinar by his presence and valuable time. Thank you, sir.
Thank you.
I would like to thank respected Principal GIT, Professor Dr. Jivananda Jana sir, and Principal Diploma, Professor Vikas Patnaik sir, for their kind support. I also like to express my thanks to Dean R&D and Dean Administration for their helping hand. I would also like to thank my HOD colleagues and faculty members and staff members for their kind cooperation and support. Last not but the least, I would like to thank all the participants for making this webinar a successful one. Thank you all. Thank you. Have a good day.
Thank you.
Thank you, sir. Once again, on behalf of the GIT family, I would like to thank each one of you for making this webinar a successful one. Thank you all.
Thank you. Thank you so much, everyone.
Thank you, sir.
Thank you all. The webinar is concluded.